Hi, I'm Jamie with Chegg Tutors. Today I want to talk to you about hydrogen bonding, an inter- or intramolecular force between hydrogen and very electronegative atoms. This is important to understanding reaction mechanisms, and it's especially important in understanding a wide range of applications in chemistry, such as why water has such a high boiling point, the intermolecular forces between DNA that allow it to act almost like a zipper, and things like why ice has a hexagonal structure. Hydrogen bonds occur between hydrogens attached to very electronegative atoms, usually fluorine, oxygen, or nitrogen, and a hydrogen acceptor, which is an electronegative atom with a lone pair of electrons. Most frequently, we think about hydrogen bonding in terms of many molecules of the same compound that are hydrogen bonded to each other to form special structures, like in ice, or special properties, like a high boiling point. Probably the most well-recognized version of hydrogen bonding occurs in water molecules. You'll note here that the dashed lines or the dotted lines represent hydrogen bonds. The little deltas represent a slight positive charge, a partial positive charge at the hydrogen, and a partial negative charge at the oxygen. This is why there's hydrogen bonding between water molecules. The partial negative and the partial positive charges attract each other via the Coulomb or electrostatic force and form a kind of bond, not as strong as a covalent or especially an ionic bond, but still strong enough to change the properties of water. The other thing of note here is that there's a very specific orientation of the water molecules that occurs in hydrogen bonding. So hydrogen bonding doesn't only change the properties of the substance that is hydrogen bonded, it also requires a very specific shape to work. Here, for example, the oxygen atoms are always oriented towards the hydrogen atoms on neighboring molecules. Hydrogen bonding is the reason that water, as the solid form in ice, has a hexagonal structure. The hexagon here is formed by water molecules that are hydrogen bonded to each other. This hexagon structure is also why ice is less dense than liquid water, and thus why ice floats on liquid water. Things like this, basically, this means hydrogen bonding is relevant to evolution. It allows fish to live in liquid water even in winter, where you would normally think that the ice would be in a solid block on the bottom of, a lake floor. Hydrogen bonding is also what connects different base pairs on the two strands of a double-stranded DNA molecule. On the backbone of the DNA molecule, which we don't see here, the phosphate backbone, the atoms are all covalently bonded. They have much stronger bonds than the atoms in between the two base pairs, which are hydrogen bonded to each other. Now, guanine, the G here, and cytosine, the C here, have 3 hydrogen bonds between them for each base pair, whereas adenosine and thymine have 2 hydrogen bonds between them. They're slightly less strongly bonded to each other. This hydrogen bond can be fairly easily broken, which is how DNA can replicate and how DNA can break apart to form single strands of DNA. But it's still strong enough that the double-strandedness of the DNA is preserved, and that double-strandedness is crucial for biology and especially for the evolution of organisms. These are a few properties of hydrogen bonding. There are many more, but we won't discuss them today. The last point I want to make is that hydrogen bonding is just one form of intermolecular force. There are also van der Waals interactions, where slightly more negative areas of a molecule are attracted very weakly to slightly more positive areas of the molecule, and also dipole-dipole interactions between polar molecules that are stronger than van der Waals forces, but less strong than hydrogen bonding. Hydrogen bonding is almost the gold standard in intermolecular forces because of its strength and its wide variety of applications. Thanks for watching, and see you next time.